I enjoy these kind of problems, so I don't want to rob you of the opportunity to enjoy them first before I go over them. But it's the I, J, K stuff. So if you wrote down stuff on that first page, the cross products of I, J, J, K, and all that stuff, then you can come up with the answer to this one pretty quickly. This one, apply a rule, and then you can use that information also. But it's pretty cool stuff, I think. Magnitudes of the cross product, two ways to handle it. One way would be to find the cross product and then find the magnitude of that resulting vector. The other way to do it would be to use this formula. Okay? There is a justification for this formula that we'll talk about soon. So for now, we'll just get into the skill of it. Magnitude of the cross product is equal to the magnitudes of the two vectors that make up the cross product multiplied by the sine of the angle between them. All right. It's one of those things where you sort of have to decide. I think number 6 was an example that I didn't like. Well, whatever. We'll try it in a minute, and we'll find out. You have to decide which is the better approach, because it is entirely possible that you might be looking at something where it's just too much of a pain to find the angle between the two vectors. And if that's the case, then find the cross product, and then find the magnitude of that cross product. Right? A good, quick place to start, U dot V. All right, because if the dot product between two vectors is equal to 0, what do we know about those two vectors? They're orthogonal to one another. All right, so the angle between U and V is equal to 90 degrees. All right. If it's not equal to 0, then use your angle between two vectors formula. All right, cosine of theta is equal to U dot V over the magnitudes multiplied. All right, so I know that now. I could find the magnitude of U, which is just 4. It's along the y-axis, you're just counting boxes. Magnitude of V, same deal, just 3. 3 units down on the z-axis, or the x3 axis if you like. So the magnitude of the cross between U and V would be 4 times 3 times the sine of 90 degrees, and that's going to be 12. Well, find a unit vector orthogonal to both A and B. See, the reason why I don't really care for this problem is because my brain is just taking me right to the cross product. I'm not struggling to. I guess you have to have the magnitude in there somewhere. It's just I don't know that I would necessarily rely on this formula. All right, well, whatever. It's a problem. So, I, J, K, 5 to -1, 0, -1, 4. Oh, sorry. Determinant. Right, so I multiplied by the cross product, determinant of the matrix that results when you get rid of the row and column that I is in. So 8 minus 1, so 7I. we have a negative j multiplied by 20 minus 0, so 20, plus a k multiplied by negative 5 minus 0, so negative 5. So 7i minus 20j minus 5k. That would be the cross product. That's A cross B. Now, the angle that separates them. If you're going to use the magnitude formula, you'd have to come up with the angle that separates these two. Quick dot product, 0 minus 2 minus 4 is not going to be equal to 0, so it's not a clean 90-degree angle. In order to use the formula, cosine theta equals the dot over the magnitudes multiplied. I'd have to find the magnitude of this guy and the magnitude of that guy, multiply them together. So personally, instead of finding the magnitude twice, I'd rather find the magnitude once. In this case, it would be the magnitude of the actual cross product. So without the formula, it would just be 7 squared plus negative 20 squared plus negative 5 squared. So 49 plus 400 plus 25, so 474. So the unit vector would be 7 over root 474 I minus 20 over root 474 j minus 5 over root 474 k. Okay, so remember, a magnitude is necessary one way or the other if you're finding a unit vector. It's a question of whether you want to find the magnitudes individually and use your cosine formula to come up with the angle, or you use the formula either way. The vector divided by its magnitude is the unit vector. So forget about that.